folks. We're on our last presenter of the day for Fundamentals Track Day 1. So the presenter that I'm going to introduce is Nishita Sant, and she's a computer scientist at GumGum. Love that name. She's involved with a number of different aspects of their business, including contextual ad targeting, image detection and classification, including, which something I found interesting, was detection of pathologies in dental x-rays, which is a potentially very big area, I think, looking at pathologies in medical images. And today she's going to talk about cloud-based vision solutions. So, welcome, Nishita.
So, hello everyone, and thank you for coming here for my talk. I'm Nishita, and I'm a computer vision scientist at GumGum. And today we'll be talking about designing scalable computer vision solutions in the cloud. So before we start, here's a little something about GumGum. We're an artificial intelligence company with a particular focus in computer vision. We invented what we call as in-image advertising here to contextually serve ads in line with content that our clients are continuously and actively engaged with. The tool on the right there is the sports valuation tool, through which we help marketers as well as rights holders capture the value of their sponsorships in social media, broadcast, as well as streaming. So, and if any of you would like to know more, we can definitely talk offline. So today we're going to start off with motivating computer vision solutions in the cloud. We're then going to move on to performance metrics. And you'll see that we keep referring back to these metrics throughout the presentation, which will make their importance even more apparent. And then we're going to do a deep dive into computer vision system design through what we define as computer vision modules and features, an API, and efficiency studies as they relate to hardware and software. So we've been talking about solutions in the cloud versus at the edge. And by now, all of us know that the answer to this question here is really not binary. It depends on a lot of parameters that we care about. So let's talk about hardware reliability. Unlike at the edge, it is your cloud service provider's responsibility to maintain and provide continually reliable hardware. Now, latency is definitely an issue in the cloud, but if your application is not going to be critically affected by minor outages in connectivity, we can definitely benefit from a lot of features of the cloud, such as the availability of a plethora of hardware and software resources, not having to worry as much about power, size, and cost constraints, and above all, like the most important application or the benefit of using the cloud is being able to create solutions that service very high volume data or throughput. So let's say we weigh in all the pros and cons, these and more, and for the purpose of the talk today, we decide to go ahead with the cloud. So as computer vision system designers, we all know this. We measure the quality of our systems based on one or more of these performance metrics. And I'd like to refer back to Mike's presentation for those who attended it, that precision, recall, F1 score, all these things really matter based on what your client wants. But another thing that I want to focus on is CPM and throughput. CPM is cost per mil or dollar value per 1,000 frames. And throughput is just your frames per second. So knowing the performance metrics that we want to optimize on, we're going to look at designing these computer vision systems in order to fulfill these requirements. We'll talk about the whys and hows of scalability, modularity, synchronicity, and efficiency. So I've been claiming that for high throughput systems, the cloud is your best bet. But why and how? And a lot of you who have already worked in the cloud know that one way of achieving this is through what we colloquially call horizontal scaling, which means that as the number of requests increase, you want to increase the number of instances that are processing these requests. Another thing that you can do is not just increase the number of instances, but you can also beef up the machines that are processing these requests. Both these together can be implemented through what we call as auto-scaling policies within the cloud. And the aim of this is to optimally utilize instances only when they're needed, thus saving you processing cycles and eventually cost. Now, before we move on to the next design principle, I'd like to quickly circle back on performance metrics. And again, I want to refer to Mike's presentation because this is really important. Say we had to design a system to detect logos, say just these 4 logos, in social media. So you collect your training data, you curate it, you label it, and say you realize a system with 60% recall and 2% false positive rate. You say, hey, this is good, I'm going to throw it in my production, which sees a throughput of 1 million images a day. And although there's no accurate way of measuring this, let's say the estimated presence of logos in my throughput is 1%. So based on our numbers, we're going to approximately capture 6 out of those 10,000 images. But what happens when you see false positives? A 2% false positive rate actually ends up being a not so interesting number for your clients. So my point here is that when you collect data and when you're training your models in your clean environment, what you want to try to do as far as possible is to have your training data model the distribution of the classes that you're going to see as close as possible to what you're expecting in your production environment. OK, so moving on. Modularity. And I love this GIF because it shows us exactly what we're trying to achieve here. Let's just go through a quick example. Say a product manager came up to you and said, hey, can we identify red Ford Mustangs in images? You're a machine learning, say deep learning engineer, say, for sure. Collect me some data, label it as red Ford Mustangs and not red Ford Mustangs. I'm going to throw it at a net that I think works best. Voila, my job here is done. I throw it in production. Everything works well. Not so fast. What happens when your product manager comes back and says, hey, that campaign ran really well. Can we now identify blue BMW Z4s? And hopefully, you already know where this is going. So at GumGum, we often end up receiving requests of this form, where we're asked to identify something very particular, and then if we do well at that, it ends up being newer requests with only a few changes. So in an effort to reducing this work for us, we came up with a concept of computer vision modules. Now, this is nothing new. The idea behind this is to be able to split up computer vision or machine learning tasks into smaller individual units of work. So here for us, they could be machine learning based, say CNNs, LSTMs, SVMs, or they could be more traditional feature matching based, could be hybrid versions, or could just be some kind of design logic. What we do is we take each of these, not each, say we take one of these units of work and throw it into, for the lack of a better name, a detector class. And along with the server, house it in an EC2 instance. Your EC2 instance is essentially the name of your compute unit in whichever cloud you choose to work with. Here, we're using Amazon. Each of these EC2 instances reside within their autoscaling groups. And each autoscaling group is associated with its respective queue or load balancer. So this unit of queue and autoscaling group is what we define as a computer vision module. So going back to our task of identifying red Ford Mustangs or blue BMW Z4s, is there a better way to solve that? say we had an object detection module that had a car or a vehicle as a class. It sends its result to a make and model classifier, and that consequently sends its result to a dominant color classifier, giving you red Ford Mustangs. So this pipeline from object detection to dominant color is what we define as a feature. Now, another important benefit of modularity is that we could have object detector implemented in, say, TensorFlow, one in Torch, PyTorch, or the other in Keras. So the idea is to give your designers and your researchers the freedom or the ability to work in environments that they are most comfortable with without increasing your time to production. Now that we have solved this problem of finding newer models of cars in different colors, the way that they can perform these functions efficiently is only if they can communicate efficiently. In order to communicate efficiently, they need to speak the same language. And we, like a lot of other applications out there, use JSON for inter-process communication. Now, two important features for this language are, one, structure, and two, scalability of the structure. When I say scalability, I mean that if you move from a detection architecture to, say, a classification architecture or a heuristic model, or even segmentation, you want to try as far as possible not to have the structure changed. So based on the ways in which we use computer vision at GumGum, we came up with the concept of a region and a property. So a region is essentially just a list of points describing a contour. Here it would be 4 points describing the bounding box, and each region is associated with its own property. Regions can also be associated with multiple properties, thereby solving this problem of red Ford Mustangs easily. Now, in the case, the way this scales is that if it was a classification problem or an image level, if we had image level labels, this region would essentially just be the 4 coordinates of the entire image. We also have a concept of subregion, which is, it has all the properties of a region, but it also gives you the space to incorporate relationships between different regions. Now, like we've talked, we have this system where we've defined modules, we have features, they can communicate as easily and well, but you still need a unit that would actually orchestrate this logic. You need something to tell each incoming request which modules to go to and where to stop. This function is performed by the API, and a few of the, I'm by no means the best person to talk about API design, but I want to discuss the features that associate with the API that are really beneficial to computer vision solutions. So one important thing is that we only saw an example of a feature that was implementing sequential logic. But there can be many applications where you would want a message to go through multiple modules in parallel, and then you do some kind of voting on the results from each of those modules. So you want your API to be able to orchestrate this logic as well. Now, another thing is SLA, or service level agreements. So if your application is limited by a service level agreement, by which it means if I, as a client, send you a request to classify an image, I'm expecting a response within a predefined number of seconds. If that's the case, you do not have an option but to implement synchronicity within your API. But if not, and by that, in no means do I say that you have the freedom to be as slow as you want, but if you're not limited by an SLA, I think, and I would suggest that it really makes sense to spend some time investigating on asynchronous options, because the first thing and the most important thing is that you can make use or take advantage of batch processing, which will help you utilize your instances even better. So talking about API design, I'll just give you a quick overview of how we've implemented it. This API was implemented using the Spring Framework, which is a Java library, and it's especially known for how much importance they have given to modular API design. Within the AWS cloud, we have implemented it using Elastic Beanstalk, which is a serverless application. And the advantages of serverless application is that it handles deployment right from provisioning, load balancing, health monitoring, and auto-scaling as well. And all this while, you still have control over all the resources that it uses. So it's not like they're going to bill you for something crazy. Like all APIs, we also have a database, which is MySQL here. And when it comes to the computer vision side of things, the reason we use this database is through Swagger to expose endpoints. Now, Swagger is an API design tool. It's a UI that helps expose these endpoints to designers and developers. Endpoints here are essentially just your computer vision features or your pipelines that help you realize newer computer vision capabilities in real time. So as soon as you log into the Swagger UI and you create your new feature, say I say, OK, my new make and model feature is going to be object detector followed by make and model classifier followed by dominant color classifier, it syncs immediately with the database, and which essentially syncs with the API, thus not having to change any code in the API and not having to redeploy the API, which saves us time and money, and even your dev to production cycle is reduced. Now, the last thing that I want to talk about when it comes to the API is the cache that we use. That's just an Elastic Cache or Redis, or just the names that are used on AWS. But essentially, it's just a cache. Why do we need it? And why is it so important when it comes to computer vision applications? So let's say that you received a 2-hour-long video of an NBA game. You just done processing it. You have the results. And then within the next 30 minutes, the same video pops up. So it's kind of wasteful to repeat processing on the same kind of media again and again. And that's essentially the only reason we use cache. There are, of course, other reasons that the API would use the cache. But from a computer vision standpoint, that's important because you're saving compute and essentially money. So all this talk about being efficient and saving money leads me to my last and final design principle, and that's efficiency, because why not? Now, in order to implement highly efficient, high throughput applications and at a sustainable cost, it's absolutely essential that we utilize the instances that we pay for to the best of their capability, obviously for a lot of reasons. Now, one way to improve utilization, you would say, is just, hey, multi-thread your application and you'll be done. But is that really all there is to it? There are two kinds of applications here within computer vision. Let's say you're using a deep learning method. So models occupy space in memory, and so do the media that you're processing. You can only have as many models loaded in memory as the memory allows you to. And you can only have as many processes as many vCPUs, or CPU threads, or GPU cores you have. Herein lies the main trade-off. You will always be capped by the lower limit between these two parameters. So essentially, what you want to do is when you spin up your servers, you want your code to be instance agnostic. By instance agnostic, what I mean is that your code should, once you spin up your server, your code should figure out the hardware of the system that it is on, and then define the optimal configuration of number of models or the number of processes that can be run on that instance. Now, the last thing about achieving hardware efficiency is managing the data that you're processing, or the media. So when it comes to images, it's relatively straightforward to optimize for images. But what happens when you're processing videos, especially those whose length you do not have any idea of beforehand? One of the easiest and most straightforward ways of achieving constant utilization over all your instances is to chunk your videos into predefined lengths and make sure that you always only process videos of that particular length and put the result back together at the end. In an effort to discuss these cost and efficiency metrics, we performed a small cost versus runtime study. Now, this study was performed on the cheapest CPU and GPU instance available on the AWS cloud, and it was done using on-demand prices. Now, on-demand on AWS means that AWS decides a fixed price for your instance, and once you agree to pay that price, that instance is yours until you decide to terminate it. So based on this table, what I'm essentially saying is that always go for GPUs when you're in the cloud. But this is not the whole picture. One main thing that I have not mentioned till now is that not all processes benefit from GPU utilization. What if you were just doing a simple voting scheme? It wouldn't make sense to spin up a GPU instance and then just do some kind of simple addition or subtraction of votes. The other thing is, within the AWS cloud, there is a concept called a spot market. Essentially, what you're doing there is you're bidding for instances. So that means that there is a possibility of getting instances for a fraction of their on-demand price, which, from experience, has brought down our production costs exorbitantly. But when you when you try to select GPUs or try to bid for GPUs, there is an issue with availability. So essentially, there just aren't in as many GPUs as there are CPUs on the AWS cloud. So since AWS cannot meet demand with supply, it just raises the price, the spot prices of GPU instances. So my point here is that whichever cloud you're working in, you want to take all of these parameters into consideration and then choose which kind of configuration works best for your environment, for your production environment. So you could work only on CPUs or only on GPUs, but you need to make an educated decision on all the parameters, all the variables that are there within your environment. So in conclusion, I'd like to recap on some of the points that I think would hopefully help you ask the right questions for your application in order to build sustainable computer vision solutions. One is client requirements. That is extremely important since they decide the performance metrics that you will want to concentrate on. Knowing these performance metrics, you want to know if you need a scalable application or not, and you want to include auto-scaling policies within your application on the cloud. We want to try, as far as possible, to be modular because it helps us realize newer computer vision capabilities faster. And synchronicity, which I think is really important. If you aren't absolutely limited by an SLA, definitely consider going asynchronous. That will really help you save money. And I'm speaking from experience. We were entirely synchronous about a year and a half ago, and we've just seen amazing results by going asynchronous. And the last thing is efficiency, because at the end of the day, we not only want to build scalable and efficient and accurate systems in the cloud, but you also want them to be sustainable. So, and that's it. Thank you.
Thank you. If you have any questions, you can step up to the mic, or do you have the mic, or is there a mic there? Can't tell. Looks like there is. There is, okay. I didn't quite follow your, and I've never looked into this before, but the costs of the CPU versus GPU. If the CPUs are slower and they're more plentiful than the GPUs in the Amazon cloud, why is the GPU so inexpensive? Is that just because not as many people know how to utilize them, or do you have any idea?
GPUs aren't necessarily inexpensive. Those studies were only on a detector and a classifier.
Oh, okay.
So in those two cases, it turned out to be cheaper. But then again, like, you need to make sure that you have a good understanding of what your computation is going to be like. So I don't know if I'm answering your question, but
That's fine.
that price also actually includes the I/O time. I did not do just a forward pass or an inference calculation. But yeah.
So do your homework, I guess. Just
Yeah.
Are there any other questions for Nishita? Now we're at the end of the day, so you might be thinking it's time to go get some of that dinner in the showcase pretty soon. Thank you very much. It was great.
Thank you.